at all the faulting systems across the surface of the Earth, as we did with that last map, and we see solid lines, we tend to want to think that there's one big fracture that separates North America from Europe or South America from Africa, but that's really not the case. And in fact, riddled across those separation plate boundaries and other locations on continental land masses are several thousands of substructural rips and tears across the surface. And my best analogy is when you rip a piece of paper in half and you look closely at that piece of paper, you're going to see little fibers. And it's those little fibers, which are tiny little rips, that actually make the bigger rip. So using the example of the San Andreas Fault system, and we think, oh, the big San Andreas Fault is going to cause part of California to fall off into the ocean. Though there's two fallacies there. One, it's not one great big break in the earth that separates the western part of the state from the eastern part of the state. That it's more like this diagram right here, where the primary fault in this case is the San Andreas, but there's thousands and thousands of smaller rifts all the way along, such as the Hayward Fault, which comes up into San Francisco and is the cause of one of the most recent large earthquakes that occurred in the early 1990s during the World Series. It was along the Hayward Fault, but it's part of this large system which actually makes up the San Andreas system. And you will note also that they're not all unilinear, which means they're all not going in the same direction. Most of these are paralleling the primary fault here, but you see funky ones like this transverse fault that's occurring right in here. We've got others that are almost perpendicular as well, that are farther away from the San Andreas. So all of this is just all of those little fibers that get ripped and torn and twisted apart as the fault is occurring. No, so that's the first fallacy. The second fallacy is this part of California is not falling off of this fault, and it's not going to then sort of sink or drift out to sea. What's happening is this part of California, and then it comes down into the Baja Peninsula of Mexico, which is right here, opens up here into the Sea of Cortez, or as we know here in the United States, the Gulf of California. So the Baja all the way up through here is sliding northward. It's attached to and part of the Pacific plate, and this side is the North American plate, and we're moving this laterally along the North American plate. So eventually the joke is that this part of Southern California, San Diego, Los Angeles are going to become suburbs of San Francisco. So there is that example. One other example for you is Iceland. I'd mentioned Iceland in the prior vignette. And unlike California, which we've got transform faults where we've sort of sliding one plate next to the other plate, we've got two large plate boundaries here. We've got the North American plate on the west side of Iceland, and we've got the European plate on the south side of our east, I should say, side of Iceland. And we're tearing a big rift in the center of the Atlantic Ocean, and that rift, which has been active and thin, has allowed magma to expel into the surface of the earth, creating Iceland proper. So Iceland is an entirely volcanic landscape made up of thousands and thousands of little fissures. Which is what we've got here. So I've got two large areas where I've got rifting taking place, this arm here and this arm here, and then this arm bifurcates or splits up here. So one might argue that I've got 4 zones of rifting. Um, so with that, this side is pushing in this direction, this side is being pushed in this direction, and all those little rifts produce all of these little tiny filaments like we saw with California, tiny little rifts all the way along. And this is what they look like. And this looks rather tiny, but if we were to put a person on here, that person would hardly be seen on this landscape. They would be quite small. So I've got very large parallel rifts. I've got several over here, another one here, and it looks like, well, I've got one coming into the screen from right in here. So this is what we've got. And by notion of this inset, we've got notation of where all of the rifts actually are mapped through here, if you're more curious. Every one of the dots, and you can see that they're so clustered and tight in some of these locations that you can't distinguish between dots, is a place where there was an earthquake. And so where we've got an earthquake is where we've got active spreading happening, where there's active movement. So we can tell here on the Reykjanes Peninsula that we've got incredible amount of activity happening. We've got a pocket right out here, which is next to the Vestman Islands, and then up here to the north, we've got 2 arms of very active rifting occurring. Currently, this is where the volcano which is erupting is taking place. So we've got on the Reykjanes Peninsula here, we've got the capital sitting right here, and right near the continental UNESCO site is where this volcano is erupting. The volcano which erupted in 2010 occurred out here, and these are 2 very different volcanic eruptions that were and are taking place. So if we look at Iceland proper, Iceland sits on the mid-Atlantic ridge. So here is the southern part of the Atlantic Ocean, with Africa sitting here, South America here. Right way up here somewhere is where we've got Iceland taking place, and Iceland is the product of this spreading zone, where we've got in the mantle, in the asthenosphere, we've got this magma welling up. It's hottest here, most viscous here, cooling, cooling, cooling. By the time it gets here, it fuses to the underside of the lithosphere. And with that, because I still have another push of magma continuing to push upwards, we're going to push and we're going to end up pulling across either side this rotational current. That pulling, just like taking silly putty, and as you pull it, or dough, as you pull it, it becomes thinner and thinner and thinner, and at some point it breaks, and where it breaks, we're going to have a release of magma to the surface. That's what's currently happening in Iceland. Is the lithosphere, the ocean crust is thin there, and because it's thin, we can then have a expulsion of magma that then gets deposited on the surface, and we create a landmass. Like Iceland, like the San Andreas Fault system, the entire mid-Atlantic ridge area is riddled with thousands and thousands of smaller rifts. So it's not one big fracture zone. It's not like a massive scar. It's thousands of little scars, some bigger, some smaller, but they're all working in unison to push east and west across. Now, this is a stylized diagram, so the scale is not correct, but what we see from here is a push in this direction, a push in this direction. Consequently, on the underside here, on the opposite side in the Pacific Ocean, the land masses are going to come together. Some of that push together is happening right here on the margin between the Pacific plate here and the South American plate. This results in subducting, pushing the heavier of the 2 plates underneath the lighter of the 2 plates. So in this case, the Pacific plate, the ocean plate, is made of basalt, lots of iron and lots of nickel, and it dives beneath the continental plate here, enters into the asthenosphere, and then we get radioactive decay, so we get some melting happening. We're adding pressure here because we're pushing more stuff into the earth here. It's got to go somewhere, and because this is now hot, it then rises and we create a puncture wound, which is going to has created the Andes Mountains right through here. So this is how this is operating. With that, where we've got rifting taking place, and in this case with the Mid-Atlantic Ridge, what we find is that we can measure the rate of spreading by that magma which emerges at the surface at those locations that are active. So the center of the ridge, which is where current spreading is taking place, is going to have the newest matter emerge. The brand new baby rock is coming out at the center. So that would be time 0 today. All right. Before this stuff emerged, the stuff that is purple emerged. So that's going to be the next youngest stuff. Think of, if this is an infant, the red's the infant, this might be a 1-year-old. So it's 1 unit older than the newest stuff. And before the red stuff emerged and before the purple stuff emerged, this layer that's diagrammed as blue was the baby stuff. So that's 3 units away from what's emerging now, and so on as we move away. So as we get to the edge of North America, out here with Labrador and Newfoundland, and out here in the UK, the oldest material is here, and here this stuff and this stuff match. They are the same age and the same material content. We're able, based on the material content and the magnetic direction of the ferrous material within that rock, we can tell how old this stuff out here is and out here is, and we can date all of each generation of material that has come through and determine how fast it took to push North America from Europe, and what parts were moving when, and how fast they were moving when they were moving. So again, here's seafloor spreading, just another example of it. So we've got the youngest stuff here, slightly older, until we reach the adjacent continental landmass. Now, at this diagram, I want to point out that ocean mass is younger than continental mass, and that's because we're always putting newest stuff right here, and we're pushing it along like a little conveyor belt. And because this stuff is heavy, it's going to subduct underneath the light stuff. So the light stuff is really old because you can't push it into the asthenosphere as quickly as the heavy stuff gets submerged into the asthenosphere as a result. So with that, with this big convective mechanism and these rotating scenarios on conveyor belts, we end up getting a series of what the breakup of Pangea looked like. So 225 million years ago, we had that really nice diagram of this zone right here. So time 1 here was Pangea. We moved to the Triassic period, which was 200 million years ago. We start to see Laurentia and Gondwana starting to form, which are 2 continental landmasses, a northern hemisphere landmass and a southern hemisphere landmass starting to form. You can see where the ocean masses are starting to now emerge that look a little bit more familiar. From 2, we come to the Jurassic period. We know the Jurassic for dinosaurs, right? We see the Southern Ocean start to emerge here. We see India is really on its way to colliding with Asia, and we start to see the split between Antarctica and Australia starting to occur. Note that North America and Europe are still joined together, as are South America and Africa. So those two splits come later, and they start to come during the Cretaceous period 65 million years ago. The configuration still looks a little foreign, but the continental shapes for some of these masses are starting to look a little familiar. India always looks like India to me. Africa seems to always look like Africa, and so does South America. But Europe and North America just look like a hot mess, as does Antarctica. And I need to be clear that when we see maps of Antarctica, what we're looking at is the shape of the ice of Antarctica. Current data lets us know that Antarctica is radically different looking than the shape that it appears on contemporary maps.